Okay, just let's repeat for the recording. So the lecture today and maybe next week also, the 2 lectures next week or 3 lectures or whatever that is, it's going to be more complicated. Well, not complicated, but it will be very technical. Not very technical, but technical in a sense that we have to prove something that we have to get our hands dirty. And so do not be discouraged. It's not very hard, and we will get back on track after we finish anyways, but we'll try to explain everything. So basically it's a hardcore computer science from 60s. So basically this is where we are at the moment. So let's just quickly recall. So we defined the pushdown automata. So these were things like this. This is the definition, right? So we're pushing, popping, doing things. We were doing a bunch of epsilon moves. And then in the end, we discussed this example when you have a string, which the languages you have a string, and that's the same string in reverse. So the idea is that you want to accept those, and of course it's generated by this grammar. So this, we discussed it last time, so let's not do this. And then we also discussed that there is a pushdown automata. We gave an example that will accept this, right? So when you see 0, you push 0. When you see 1, you push 1. Then you, by miracle, guess where the middle is happening, and then you start popping, and then you will end up with an empty stack, and the word will be completely red, and then you will accept. So this we discussed last time. So now this is where we so here is the drawing of this thing happening anyways. So now we start the thing I mentioned. So we have to prove maybe like 4 things. So let's see. So the first lemma, let's read it. It says that if you have a context-free grammar, right, so it obeys the context-free rules, then you can construct a machine, non-deterministic pushdown automaton, that accepts exactly this language, the language that is generated by this grammar. So now you have to also prove the opposite. So next week we will try to prove that if you start with a machine, then you can construct a grammar that builds the same language that this machine accepts. But each one of these proofs have 3 parts. Why? So in here, like you have a grammar, you're constructing machine. So first you have to construct this machine. This is your first step. I give you a grammar, you construct a machine that simulates this grammar. Then you have to prove that if the word is in the language generated by the grammar I gave you, it also must be in, let me get the laser. So it also must be in the language accepted by the machine you constructed. Then you have to prove that if the word is in the machine, so it's accepted by the machine you constructed, it's also generated by the grammar. So if I prove these 3 things, the half of the thing will be done. Well, it will prove lemma 5, but by half I mean that this is, so for today, the setup is I have a grammar. So you gave me a context-free grammar, and I'm building a pushdown automaton, right? As we did in previously, we had if I gave you a regular language, you were building an NFA. Remember, we were using epsilon moves. This is what we're doing now. We're building a machine. And this gets, well, this is not very technical. The other side is more technical maybe, but it's not that, I mean, it's technical, but it's not really hard to understand or anything. So, okay, so I'm building a machine. You gave me a grammar. So you have, I have non-terminals, terminals, production rules, and start symbol. Those production rules are such that I have 1 letter on the left and anything on the right, right? It's not in a Chomsky normal form or anything. It's just a general context-free grammar. And so I construct my machine. First, I have to tell you what is the alphabet on the tape of my machine. It's exactly whatever are non-terminals for your grammar, of course, because words consist of non-terminals, so I should be able to accept those words. So of course, the non-terminals you give me will be exactly what my machine can read on the tape. So this is the first. Now, what can I write on my stack? I declare that my stack alphabet is exactly your non-terminals and terminals. So I can write non-terminals and terminals on my stack as well. And you also give me productions, right? So there are finitely many productions. This is the definition of a grammar. And I number them P1, P2 up to Pn. So I give them numbers. And so each production I now will consist of one letter, one non-terminal on the left. I call it Ni. And then Gi many symbols on the right. So let me enlarge this so you can see. So there's one, because it's context free, there is just one letter here. I call it Ni. So P4 will have N4 on the left, whatever this letter is. I just call it N4. And then it will have X41, X42, however many, whatever the length is here, I will just call this length Gi. Right? So it's a function that depends. So this will have, all Gi's will be different for different I's. So G4, for example, will be, if I look at production 4, this will be like N4 implies X41, X42, X43, X45, however many X4GI. G4 in this case. არა, ეგ იყო Chomsky normal form. მაგაში შემიძლია ეს მივიყვანო, მაგრამ არ მინდა. It's just completely general now. What I'm going to do is basically what a non-deterministic pushdown automata is going to do. It is, so you give me a grammar, right? And so this grammar generates some words. How does it generate a word? It creates a derivation tree, right? You derive this word. What I'm going to do, I'm going to simulate the derivations on my stack. That's the idea. So I will push derivations on my stack, and then I will pop things when I read the letter. So you'll see how it goes. So these are my productions, and now I use an extra state. I will define a state R. I haven't defined states yet, but I will have one state R, which will be to guess what production should be applied next. Somehow. So imagine I have a word, and I have to guess what was the derivation tree. And basically, I'm doing all possible derivation trees because it's a non-deterministic thing. This is basically what's happening. So initially, so how does my machine operate? I haven't given you states or anything yet. You will see along the way what the states are. So initially, so I'm in start state Z0, and without reading a tape and without looking at my stack, I just go to state R and push S. So S is included, so S is a non-terminal, it's a start symbol, so it also can be pushed on my gamma. So now I saw the word, I'm supposed to accept it if it's generated by a grammar. So I saw the word, I didn't look at it at all, I just went to state R, whatever this R does, and I put S on my stack. So in the beginning, there's just one thing, S, sitting on my stack. So now what I'm doing? Now I'm choosing a production PI, matching the top symbol of the stack. That means that let's read what it means. So if I'm in state R without reading a word, if I see non-terminal N on my stack, what I can do is I can go to some state Ri, dependent on what I see. So if I see Ni, I will go to state Ri. If I see so on top, if I see N7, I'll go to state R7, and I will do nothing on my stack. So initially what will happen, I will see the word, I will push state S, so I will push a non-terminal S on the stack, and then when I see S is also, maybe there is a production. So let me go. So if there is a production, let's say S implies this is just an example. AB, whatever, ABX. Maybe this is my production. Then this will be one of the production rules. Maybe it's P2. Because I numbered all the productions, maybe this is P2. Then I call this guy basically N2. Because this is how I defined it. So I call this guy N2, my start symbol. And when I pushed it on the stack, so S is now on my stack, my machine is here, it's reading a word on the stack like this. So initially, it will go to state R2 in this case. And what it's supposed to do, what I want to do is I want to replace this thing by something like, so I want to replace it by XBA, something like this. So let me see if it's the correct direction. So what I want to do is when I see the start symbol, I want to replace it by a production, the right side of the production like this. So this is the idea that I want to do. And for this, I use this states Ri. So from this state R, I go to state Ri, which depends on what I see on my stack. So if I see S, I will go to state R that corresponds to S, to production, concrete production that S produces. And then what I want to do, let's not look at this because this is technical for a moment. What I want to do, I want to replace on my stack this symbol S by the right hand side of the production. So in my case, this is X21, this is X22, and this is X23. So I want to replace this with XI1, XI2. So I want to apply a production, but it's written on my stack. Somehow, if you imagine that your derivation tree, your word as being derived by a tree, your stack kind of stores the levels of this tree somehow. So it will replace Ni with the right hand side of the production. But how are you supposed to do the replacement? This is the idea. So if you're in state Ri, you do not. I have not read the word as of yet. So I'm in state Ri, I do not look at the word, and I see Ni sitting here. What I do is, if the right hand side of the appropriate production is epsilon, meaning if this was happening, if this production were supposed to be used, this is what I'm claiming, then I just remove my S. This is what this guy does, and I go back to state R. In other cases, when the right hand side is not empty, then I go to a different state, again, Rigi, whatever this state is, and I remove one symbol, and then from this different state, again, without reading the word and without looking at the stack, I start pushing this Xij's. So let me pause this and so to continue, so exactly as you said, so what I'm doing, I'm replacing all non-terminals that are sitting on the top by production rules. But now, if I replace my X, so this is the effect, basically. So the effect is written here. Let's erase all this and let's enlarge this. So if I do this, this is technically, I'm using this intermediary, you can look at it, stare at it for some moment. So you're using intermediary states to somehow push this right-hand side of the production. And the effect is this. So if you were in state R and the word was written up there and your stack contained Ni on top and some alpha, some string below, what will be the result? The result will be you will still be in state R because you always return to the state R, see? After you finish pushing, you return to state R. So you will return to state R. Your word will be the same because you never read the word. See, it's always epsilon here. You never read the word. And instead of Ni that was sitting on top, now you have the right-hand side of the derivation that followed Ni. And alpha will be unchanged, the thing that was sitting at the bottom. This is all that happens. Basically, I just replaced the top symbol by the right-hand side of the derivation. So if this derivation exists, this computation will also exist.
do we recursively do this until we get only terminals on our stack? Or do we just, what if like S derives non-terminals?
So if S derives only non-terminals, that's what you're saying? So exactly, so as we explained, so the effect is this. So you just replaced ni with some string, which xij's can be terminals or non-terminals, but next what we do is we cancel matching terminals, meaning that if I'm in state R, as you remarked basically, so if you're in state R and I see T in my word, so terminal T, and I also see T on top of my stack, what I'm supposed to do, I will stay in the same state R, but I will remove this guy. So I will pop off all the non-terminals that are sitting on the top. So in our case, when we had this, so when we had A, B, and X, so if the word that I'm reading contains A and B, I will remove A, I will remove B, and then I'm stuck at X, and I can again use the same pushing method on derivation. And the intuition already tells us that I will only go through the complete word, and my pushdown stack will only be empty if the derivation tree exists. That is the idea. So you're popping it off here, and the effect is that if you're in state R and there's some non-terminal here which followed with some string and some non-terminal here on your stack followed by some string, those non-terminals will be removed in the configuration. So this is supposed to work. So this is how you construct a pushdown automata from the grammar. So it has all the possible. So basically it stores all the possible derivations in the stack. That is the idea. And you can read the derivations from left to right somehow. That is the idea. And so here is but we have to prove that this works. So there might be, the same word can have many different derivation trees. That is correct. So what I'm doing, I'm taking all possible, I'm a non-deterministic guy. So every possible use of the production is a possible computation. However, the only computation that will go through is the one that is the derivation tree.
So we are proving that there is at least one derivation.
Exactly, yes. There might be a couple derivations. So if there are two derivation trees for the same word, this means there will be two different computations that go to an accepting state. So okay, so we had so now we have to prove this. We have to prove the following, so we have to prove two things. First, that if the word is in my grammar generated, so in the language generated by a grammar, it's also in this accepted by the machine I just constructed. And I have to then prove the vice versa. But let's try to first prove this. So let's say the word is generated by my grammar, and I want to prove that it's accepted by my machine. So for this, I will prove the following. Pay attention. So let's say I have two strings of non-terminals. Right? So I have W and beta. These are two strings of non-terminals. And let's say in this V or nu, let's call this guy V. This V is either a non-terminal or a terminal. It's like a single symbol of non-terminals or terminals. And let's say V derives W. So in this case, this is basically non-terminal. But let's say V derives W by a derivation tree of depth T. So this is the setup. So say V is non-terminal here. It cannot be a terminal if it derives something? So V is non-terminal that derives W, and if it derives W, this tree has a height. Let's call this guy T. So it derives with a height T. Then what I'm claiming is that if I start in R, in state R, and there's W written and then there's beta. So I'm looking at the first part of my word, so the part W of my word like this. And V sits on top of my stack, so symbol V sits here, right? And there's maybe alpha underneath. What I'm claiming is that once V is removed, W is also read. So if V derives W, then I will read W and remove V. This is how my machine works. This is what I intended, and I'm proving that this works. Why does this prove the claim? This proves my claim because the following. How did I define my machine? I started in state Z0. The W was completely written out. This was my word, and there was nothing on my stack. This is my initial configuration. The next configuration, remember, I moved to state R, did not do anything with the word, and pushed S. Now I'm in this configuration, state R, W, S. Now, if my word is in my grammar, that means there's a derivation tree that starts with S, right? So it starts with S and derives W, if my word is in my grammar. This is the definition that word is in the grammar, in the language generated by grammar. It means that you start with S and there's a derivation tree. Then this lemma would tell me that I have R, my beta is empty. So if I take beta B, this works for every beta. So if I take beta empty here, and I take alpha empty as well, but for V I take S, then this tells me that this machine will end in state R, beta and alpha, empty, empty. So it will end up in a state R with empty stack and empty word. So if I prove lemma 6, I prove that I start here and I end up here, and I will just make my R an accepting state, and then I will accept. So basically, if you look here, this is just a general version of what I need. I need even less than this. This just says that if I read part of the word, I will pop the thing that derives that part of the word. This is basically what I'm proving. And then if for this I substitute with S, and for word I substitute the whole thing, then I will read the whole thing if it's derivable from S. This is basically what I'm trying to prove. So we're considering for any beta and alpha, but we really only need, if we take beta is empty word, and alpha is also empty word, and then I will just declare R to be an accepting state, and then my machine accepts. So why did I introduce T at all here? Well, what does the depth of the tree tell me? It should, what it tells me is I'm going to do an induction on my, how do I prove this? First I will prove it for, let's say T equals 0. So T equals 0 means that V derives W in height 0. That means V and W are the same. There's no height to the tree. There's 0 height, so V and W are the same. If V and W are the same, W is just a string of non-terminals. V is just a single symbol. That means that V and W are both just a terminal symbol. Oh, this is why I need terminals here for this case. So if T equals 0, then V has to be a terminal. This is why it's written. In all other cases, it will be non-terminal. So this is a boundary case. When your height is 0, then V has to be terminal also. So this is why we need it here. So this is correct. So if T equals 0, V and W both are terminals. And by construction 3, remember, imagine V is terminal here, W is also terminal. They will get matched and popped off. So it will, the next configuration, well, next or whatever, the configuration, the following configuration will be something like this. So this will happen if they're equal, because by construction 3, we are just canceling matching terminals. So this is T equals 0 is not a problem. So now, the more involved thing is, let's say this is true for if the derivation tree is of height T minus 1 and less, and I want to prove it for derivation tree of height T. Well, first I look at the special case, right? If my W is basically epsilon, so meaning that V derives epsilon. So if this is my rule, then by construction 2, remember this is the construction 2, this V will just get popped off. Because what I'm doing, I'm basically pushing the derivations on the stack. So if my right sides of the derivation on the stack, if the right side of the derivation is empty, what will happen is it will just get removed. So if GI is 0, this special case, if you do not understand what's happening here, you just have to stare at this for a moment and that's it. You just remove the V. So here you will have V alpha, W will be empty, and you will remove V. This is what will happen, and you will get to R beta alpha. So this also works for this special case. The interesting part is this here. So this is the part where this is not just a trivial derivation, but rather V derives W in height T. Look now, look what's happening. Let's try to understand this at least. So I start in state R. My word upstairs is, look at this picture, it's W and then beta. And my stack is just V and alpha. So the stack is V and alpha. Let me get my laser. So the alpha downstairs and V up here. And I want to get here. I want to read W and pop V. I want to prove that this happens. Okay, what happens first? So what happens first is V is replaced by derivation. So not the derivation, V is replaced by production. So what will happen first is, so if this is my derivation tree, right? V on the right side will be replaced by the first level of my tree. Because it starts with V, it derives W. The first level is X1, X2, X3, whatever. So first thing that will happen on my machine, the V can be replaced by X1, X2, or whatever. So these guys will be pushed Xi1, Xi2. So this is my derivation tree. This is V, which is one of the NIs, but doesn't matter. It's V. The height is T. The first thing will happen, here you see, V is replaced by Xi1, Xiji, so by these guys here. And then, I know by induction, when now this guy derives a portion of W. This guy also derives a portion of W. So if I have a derivation tree like this, there is V here, and then there is W here, and there is like, let's just call it X1, X2, X3, ... maybe Xn. This derivation tree continues like this, right? So there is a portion, let's call it W1. This is a part of W that is derived from X1. This is just basically definition of my tree. And if the height of my tree is T, the height of this guy is T minus 1. And if the height of this tree is T minus 1, I know that my machine will erase this guy, will read the first portion of W and pop X1. So what really happened, I had V, I replaced, so I had this derivation basically, X1, X2, up to X, whatever, let's call this N, like this. And then, ... I went to W. This means that X1 actually derives a portion here. And if X1 derives a portion of W, I know that in my machine, when I replaced V with things like this, X1, X2, X3, ... Xn, this is my stack after one step, after V was removed and this was replaced by construction, then I know by induction hypothesis that this guy will be removed and the W1 will be read. This is what I'm trying to prove, but by induction hypothesis, and then similarly X2 will be removed and W2 will be read. And I will go all the way to xn, all of them will be removed, and the whole w will be read. This proves the claim. The only part that I use that is the construction that the first step of removing v and pushing x1 to xn is just, this happens by construction. This is all this proof is really saying, that you start here, by construction, you remove v and push x's, and you can write w as a composition of smaller w's, such that each w1 is derived by xi1, w2 is derived by xi2, and so on. And by induction hypothesis, you can remove xi1 and w1, and you can continue doing this until you reach this guy. And then you just declare your accepting states to be R, or this, if you have an epsilon also in your language, Z start state. So this actually proves the claim. So let's ask questions now. Do you understand how the machine works, right? You basically push all possible production and it's known. So if you have a derivation tree, then your machine will basically go through. This is what we proved now. If there is a derivation tree, your machine will go through. But now I have to prove that if my machine goes through, I have a derivation tree. This is what is to follow, is that this is even more convoluted proof, that if my machine, if my word is derived in, so it's accepted by my machine, there is a derivation tree. There is a trick here. So let's look at this trick. Yeah, 10 minutes is not enough, but let's at least understand what is going on here. So let's say my word is accepted by my machine. If the word is accepted by a machine, this means that there is a computation that starts with Z0, the whole word written on the tape, and nothing on my push down. So this starts here, and it ends in state R and epsilon epsilon, because R is the only accepting state unless your word was empty. So this starts here and ends here. If my word is accepted. Now, this is the trick definition here. Let's say K is one of those configurations here. And let's say K is of this form. Let's say I'm in state R. I already read some words, some letters. I don't know which ones. So there's some string mu left to read. And P sits on top of my stack. So this is my state. I'm in state R. I read some letters and mu is left to read, and P sits on top. P is non-terminal, terminal. By NK, I will denote, and I will ask you a question now, a first configuration after K. So then I have to end here somehow. So I start at K0 and I end here. And in the middle, I'm here somewhere. So I would denote the first configuration after K, such that I'm still in the same state R, and my P is removed. There might be many, so I'm in some state, the word is left, and there is P here. It might happen that I replace P with some other things, I move around in different states. But if I return to state R and my P is removed, and this is the first time it happens, I call that configuration NK. And this has to happen because in the end I have to remove everything from my stack if the word is accepted. So if everything is removed, at some point P is also removed. And I must come to state R. So I must be in state R with P removed at some point. This might be the last state also, but let's say it's not, and I call this guy NK. And tau K is a number of steps between K and NK. And we'll do an induction on tau K. This is a very smart way to think of a thing to do an induction on. So if you have an accepting computation, just to repeat, then if you look at the state that starts with R, there is M on your tape and P on top of your stack. There has to come a point when you're still in state R. You read some letters, I don't know some of them, but P is removed because everything has to get removed in the end. So P also has to get removed. And the first place you remove P, you call NK, and the distance between K and NK is called tau K. So now, since we do not have much time left, I will just read out the lemma. And so the lemma says the following, and then I will highly advise you that before next week to at least understand the things we covered during this hour. The lemma here says is that if you're in state R and your word on your tape is mu beta and V sits on top of your stack and NK, the next configuration where V is removed is this, right? Then V must derive mu. So it's the opposite of what we proved. Here, now I'm saying that if I removed V, then I read mu. That's basically what I'm saying. Before we had, if I will read mu, I will remove V. But now I'm saying that if I removed V, and it's the first place I removed V, then I had to read mu. So, well, it's kind of bad wording. So what it says that if I removed V by reading mu, then V derives mu. So this is the complete opposite. And it just says that this claim follows if we take alpha beta equals epsilon, the claim that this follows. And I actually wrote down the explanation why this follows, and it's also in your slides, but I advise you to think about it yourself. Why does this claim follow? This is a good exercise to show, to kind of understand if you understood what's happening or not. Okay, let's finish, and I will highly advise you to look at it because there's even a meaner proof coming.